Hello, I would like to introduce our paper, Multimodal Variational Auto-encoder based Audio-Visual Segmentation. My name is Yusun Mao, a PhD candidate at Northwestern Polytechnical University, and my collaborators in this work are Jing Zhang, Machu Xiang, Iran Zhong, and Yuchao Dai. This work focuses on a newly proposed task, audio-visual segmentation. Given a video sequence with audio, the task aims to segment the objects being sounded in the video, referenced by the audio information. Existing audio-visual segmentation methods employ implicit feature fusion via audio-visual cross-attention. These methods purely rely on fitting the discrete samples in the dataset, and there are no constraints to guarantee the contribution of each modality. We propose to model the latent distribution of each modality via a multimodal VAE. Our contribution can be summarized as follows. First, we introduce the structure of our model. The model contains three main modules: a visual feature extractor, three latent space encoders, a multimodal fusion, and a segmentation decoder. The feature extractors are used to extract backbone features for the two modalities. We also design three latent encoders to achieve latent space factorization and obtain both task-driven shared representation and modality-related specific representation, achieving explicit multimodal representation learning. The decoder is introduced to get the final segmentation maps, indicating the sound producers of the audio-visual data. As mentioned above, the latent space encoder is an important module of the model proposed in this paper. Here, we show the specific structure of the latent space encoder used in this paper. Each encoder consists of several simple convolutional layers, which ensures the lightness of the whole model without adding too many extra parameters. To ensure the effectiveness of the latent space factorization strategy proposed in this paper, we guarantee a meaningful representation of the latent space and ensure that the factorized subspace contains task-driven shared representation and modality-related specific representation. We designed several different latent space constraints. First, we add JS divergence to ELBO to perform a trade-off between the computational efficiency of the inference process and the predictive quality of the generation process of VAE. Further, we introduce a representation orthogonality constraint to ensure that the modality-shared and modality-specific representations capture different information within each unimodal data. Finally, we introduce mutual information maximization as a regularizer to measure the shared information between the latent vectors. We have trained as well as tested on the AVS bench dataset and present qualitative as well as quantitative results here. From the visualization we can see that our proposed method achieves better audio-temporal and spatial localization quality, leading to better segmentation performance. Meanwhile, from the table, we can see that our method has a substantial performance improvement compared to the baseline. And it achieves the state-of-the-art performance. Further, we show here a video demo. From this, we can see the superiority of our proposed method. We show here the results of the ablation experiments. In this paper, detailed ablation experiments are conducted for each of the proposed components. We use the TSNE method for latent space visualization. The visualization in high-dimensional space intuitively demonstrates the process of modal factorization and the effectiveness of various constraints for better latent space representation. We performed additional analyses that demonstrate the superiority of our proposed model in terms of pre-training, and has a smaller number of parameters as well as a lower inference time. Here we make a summary. We propose an explicit conditional multimodal variational auto-encoder, ECM-VAE, for the audio-visual segmentation task, with meaningful latent space modeling, shared and specific representations factorization and finally achieving fuller use of the audio information. Our model demonstrates the effectiveness of multimodal latent space modeling and can be used as a base component for multimodal scene understanding. In the future, we will explore more multimodal fusion and larger-scale multimodal modeling. Thank you for watching. Feel free to follow our project page and ask us questions.